Swayam Prabha. Digital India. Educated India.
Welcome to lectures 4 and 5 of week 7. The last two lectures of this particular week will be combined because now we are trying to get into the business end of the perforated things, which will also continue for the entire week 8 and some parts of week 9. This is probably one of the very important muffler components. Actually, that is like we were discussing towards the end of the last lecture, that most of the mufflers, almost all of them, have some sort of a perforated element to guide the flow and not allow the flow to completely expand, and which will cause a lot of flow induced noise problems, and that will be counterproductive. So that is why we put a lot of focus on analysis. So this class, what we are going to do, week 7 and lectures 4 and 5 of week 7, they are combined. So now in this week, what we are going to do really is analyze two duct perforated systems. We will talk about the development of such equations right from the control volume approach and point out terms which really lead to the coupling of waves. In all our analysis, as we have been doing so far, we will be considering only the planar wave propagation along the axis of the duct. So that is what we are going to do. And let us see how we go about it. Well, to begin with, what we will do, let us consider, so let me write down this class, the objective of this class, two interacting duct system. So different configurations that are possible. We will also do review, very briefly though, review perforate expressions that is developed by people over different times, perforate expressions, and then we will possibly try to solve one example, I guess in MATLAB, of a fully perforated CTR. That is, what is CTR? It is concentric tube resonator. Concentric tube resonator. All right. So let us analyze different systems. So here we are. So all these figures, this set of figures, what they really show you is a typical concentric tube resonator, CTR. That is what it is called. C here, T here, and R. Later on, probably sometime in the beginning of week 9, I reckon, we are adding an extra C, that is your conical concentric tube resonator. What we, I just kind of briefly alluded to that in the last week's lectures. So for now, let us keep the discussion very simple. We have basically this is nothing but it could be in principle, this is a circular duct, this could be circular outer section or a circular chamber, or it could also be elliptical in principle. Lot of commercially used mufflers are also elliptical in shape, but does not matter as long as you are considering planar waves. The cut on frequencies depending on the cross section will change, of course, but the main idea is to analyze the coupling that happens between the inner pipe, let us say 1, and the outer annular cavity, that is the outer cavity, this guy. So when planar waves propagate, so there are different elements. So before we analyze different elements, let's let's first talk about what happens. So this is a schematic diagram of a concentric tube resonator. So this is partially perforated. So and clearly you can see neck extension. So suppose this guy were not there. Suppose this part is not there. So you would get back your simple extended inlet and outlet element. So this perforated bridge, what I was mentioning in the last class, this acts like the real purpose is to guide the flow, but in the process what it does is basically the flow, as the flow passes through it, the waves that are generated, the incoming disturbances that occur from the engine that propagate downstream of the engine, they get a chance, they get an opportunity. Note that this is a solid section, these waves. So, the waves cannot interact directly with the annular cavity in this region. It is only when the waves, when they approach this perforated section through the small holes, something like this, they get a chance to go out of these waves and interact with the annular cavity surrounding it, isn't it? The waves are interacting now. So, basically by now you can sort of very well guess what is happening in the duct 1. So, it is a planar wave propagation, and in the annular cavity you can also consider a planar wave only. So, when you mean planar waves, you really mean this kind of a wave front, and here you mean this kind of a thing, isn't it? So, where does the magic happen? How does the coupling happen? So, one thing that I mentioned at the very outset, at the very beginning, is that coupling between the planar wave propagation here in the duct 1 and the annular cavity duct 2 really happens through the mass exchange, that is basically from the continuity equations in each of the duct. Because of the annular cavity, some part of the fluid is going inside the control volume here, we will do a thorough analysis, and some part can also come inside. So, it is like the exchange between the acoustic masses, exchange between the ducts 1 and 2 of the acoustic masses leads to an additional term in the continuity equations in each duct, duct 1 and duct 2, and we will see how this kind of affects the development of equation. We will have 4 first order linear differential equations, and you can sort of couple them or combine them into eliminate some variables, velocity variables, acoustic particle velocity, to get 2 coupled second order linear differential equations, ordinary differential equations, but they are second order and coupled in P1 and P2, P1 tilde, P2 tilde. So, that is what happens, and note that this can be, so this partially perforated bridge, certain length L, this is exactly like a counterpart. This entire configuration what you are seeing here, this one, this is like a counterpart of your this configuration, isn't it? So, now if we were to make this thing fully perforated, what would have happened? So, and especially when it has a high porosity as we are discussing, so that would basically act like your expansion chamber, a concentric expansion chamber, but it would still be 1000 times better than just leaving it aside, leaving it just like this because of flow separation, because even if it is fully highly porous, but it is fully perforated, it would do its job, at least it will provide you some attenuation, it will not be counterproductive. So, that is one thing, we should be able to analyze such things. So, apart from all these, there are other elements also which is kind of shown in these figures. So, this is now one thing before I just sort of forgot to mention that in this configuration that we are seeing here, hang on, here we are seeing that the flow is going like this. So, so there is a flow in the central duct, or it is also called airway. This duct is also called airway. Okay. So, airway definitely has a flow, mean flow along the z direction, or and it is typically, although it has a profile something like this with boundary layers formed, we will consider it like a plug flow only. Now, but however, in the annular cavity, we for at least for this configuration CTR, whether it is a partially perforated or fully perforated, does not really matter, we are assuming there will be no flow, 0 mean flow. That may not be 100% correct, there might be some mean flow at least in these regions. Annular cavity definitely does not have mean flow, but in the middle of the section, depending on the length, you could have some non-zero mean flow. One really needs to do a CFD analysis to resolve the steady state flow fields, maybe RAN simulation or something like that would help to resolve the flow fields. So, now that is what is happening, but for our cases, to keep our analysis, plane wave analysis simple yet reasonably accurate, we will assume, at least for this configuration, 0 mean flow. That is basically, let me sort of write it. If you have a mark or velocity u naught here, uniform velocity, all this region, in all these regions we have 0 mean flow, that is u naught or u2 is 0, capital U2 is 0 here. but capital U1 is some value here, typically less than 0.15 or so. There are other configurations also, like it is called a cross flow. The difference between this one and this guy is that flow just grazes in this surface, and so it is called a grazing. So, whatever perforate impedance expression zeta what you will be seeing, that will be for a grazing flow. Grazing flow just grazes the surface, grazing flow impedance. For this one there will be a cross flow, because the flow, this is like a dead end, this really is a dead end. The flow, the flow is left with no choice but to go through the perforated tube, and then it sort of interacts with the outer cavity. So, here in these, you can do some lot of simplified analysis, but what I am saying is that for the cross flow configuration, in the annular cavity assume the flow to be 0, but in this part there could be some non-zero flow. We probably can assume some reasonable values, and in this part there will be flow, and the flow will be distributed like this. But the essence is that the flow has to cross over, and that is why it is called a cross flow expansion chamber. Similarly, here also the flow has to come out of the cavity, mean flow, and it is called a reverse flow expansion chamber. This is yet another configuration, cross flow contraction element. This was an expansion, this was a contraction, in the sense that the flow has to come, it meets a dead end. Before it does so, it has to go inside. So, we assume certain suitable values of that, and here we have a reverse flow contraction element. So, that these are really building blocks of the much more complicated stuff that I had shown you in the last class. So, because combining all this, one can really very complicated muffler system with certain desired transmission loss and all that. But in all the configurations, B to E that is shown here, configurations B to E, we must use expression for perforate impedance which has a cross flow impedance, cross flow impedance. Okay, we must do that. We will probably look at it in the next week's lecture. For now, let us get back to our main thing, which is your CTR, concentric tube resonators. All right, let us get to that. So, how do we begin our analysis? Let us draw a simple figure. So, basically this is, let us say this is your annular cavity, and inside you have a perforated section which is something like this. You have holes here. So, if you go back to your last slide, analysis of this particular part, this, all this is simple. We have, by now you should be a little proficient in analyzing that. This is like a minus j y naught into cot k naught L A. Similarly, this is minus j y naught into cot k naught L B. The impedance is seen here, and then you have tubular elements or transfer matrices. Main thing what you have a fourth order differential equation if you were to combine things, but then there are simpler techniques of using coupled analysis of second order ODEs. So, we will soon get to know all that. So, this is an element, a fundamental element what we will consider now. I am considering this guy as 1, this guy as 2, annular cavity. So, how do we go about analyzing this thing? And here of course, I am assuming, like I said, a mean flow U naught. So, let us begin with considering the continuity and the momentum equation in an element in a small control volume. Let me sort of do an exaggerated version, which is your this thing. So, we will consider a small control volume and analyze the flux that comes in, the flux that goes out, and what is the flux that is going out through these side surfaces or the cylindrical surfaces. So, that also has to be accounted for. All this was not there. You might have to go back to your week 1 lectures to kind of contrast this with the derivation there. So, in that case, for a 1D case at least, there was no flow through the cylindrical surfaces, there was only 1D flows. Okay. So, that is how we led to the derivation of the 1D equation. Okay. So, now in this case of course, we have flow through the cylindrical surfaces also. So, we need to account for that. So, let us quickly write down the fluxes that one would sort of get when such a thing is considered. So, Now, here I am assuming, let us say this is rho, this is your, let the density be rho, and this is your cross section area, let me call this S1. S1 is all uniform. By the way, S1 and S2 are uniform with distance Z. So, this is Z, S1 and S2 are uniform with Z. Okay. So, rho into S1, and this element is, let us say, delta Z. So, what is the flux that goes inside this thing? So, this has a unit of kg by meter cube, this is meter square, okay. And velocity you need to multiply, isn't it? Let us call this velocity u1. So, this has unit of meter by second. So, these guys cancel, you are left with the unit of kg per second. So, that is your mass flow rate, rho SU. Remember your elementary fluid mechanics. So, rho S1 U1 at Z, and the one that goes out from the opposite surface is also pretty much the same form, but this is evaluated at Z plus delta Z. Okay. So, the flux, basically density into the cross section area into the velocity, that will give you the mass flow rate. So, the difference of that will give you the net mass flow rate. So, basically I guess I have to use another slide. So, the one that goes inside in flux is rho S1 U1 Z, and the one that goes out is rho S1 U1 Z plus delta Z. Okay. So, but so that has to be balanced with the net change in the mass flux within this control volume with time. But before we directly jump on to writing that expression and equating things on the both sides of the equation, we must also remind ourselves that there are things that happen now from this surface. It is like a porous or permeable surface, this perforates. That is, basically there is one thing I want to make a very small digression. They are basically there are different approaches of dealing with perforates. The one that we will be following, and what others have also followed throughout the literature, throughout this development of perforates, is that this surface is considered as a kind of a porous surface with certain porosity. It is like a permeable surface allowing waves to go through them, with a certain some sort of a resistance or impedance, what we call. So, it is like wherever we have a perforate surface, we take the difference. We often define a quantity named as a difference in the perturbation pressure across this element divided by the normalized velocity, that is rho naught C naught into u, which is assumed to be constant across this at the interface. So, this ratio is called the perforate impedance. It is like the waves are attributed, they are allowed to go through the surface as though the holes kind of serve the purpose of making the surface very permeable, or allowing the waves to go through that. But then there is also yet another approach in which these perforates, these small holes that we are seeing, they are like small cylindrical necks, and outside the annular region is a big cavity. So, in a way you can consider, well, there is more thought to it, I mean more analysis needs to be done, but you can consider wave propagation through individual such holes through a very complicated analysis by considering wave propagation through each of these holes and analyzing that, and maybe as a array of resonators. But this the approach that we are following in right now is very easy and it's used a lot. The other approach, well, I am not quite sure of that, people might have done it, but this is the most sort of popular approach of modeling the perforates by means of an impedance expression. It is like taking it like a permeable surface. So, anyhow, coming back to the discussion, the waves that go through this surface, I mean what is the mass flux that goes out. So, what is the cylindrical, the curved surface area of the cylinder. So, this is your, let us say the length, obviously we know delta Z, and let us say the diameter is d1 and the outside diameter is d2, small d2. Okay. So, what is the curved surface area of this guy? That is your pi d into d delta Z. Pi d is the circumference multiplied by delta Z, which is your elemental length. So, this is the area and rho is the density into u Well, we need to use some different variable. So, let us call this as u star. Now, again this one another thing that I want to talk about here is that we will eventually linearize this equation, we have not done that so far. So, u star will not be having a mean flow component, it is just a perturbation velocity, because it is like the acoustic mass that is being going out or coming in inside of this volume. So, u star is basically very small, it is orders of magnitude smaller than the mean flow velocity whatever is present. So, in a way u star is really your acoustic particle velocity, but in the radial direction, right. So, this is your if you draw in sort of an isometric view of this, and so it is something like this, along the radius it is going, otherwise u1 is going like this, u star is going like this. So, anyhow, so the point here is that this mass, this particular guy, this needs to be sort of added to this equation. So, basically the mass that sort of leaves this thing is also your rho pi d into delta z into u star, all right. So, this then must be balanced by the net changes of net temporal change. So, what is the total mass that is present at any time in the control volume? That is your volume rho s1, and this is d1, sorry. So, this is also d1, rho s1 into delta z, that is your volume times density. So, time change with respect to this, okay. This is what you get. Now, let us do one thing, let us divide throughout by this guy. So, we should also divide the entire thing by delta z first, and or probably we can divide throughout by S1. Let us do that first, and so what we do, dividing by S1, we will get u star is equal to rho delta z t. Now, we again divide throughout by delta z. Here we get minus u1, because now this becomes your partial derivative with respect in the limit of delta z tending to 0. Here we divide throughout by delta z, so this guy goes away, this guy goes away, okay. So, we do that. So, now as a result, and we take the limit delta z tends to 0, okay. So, then we get this guy inside this bracket, plus you have minus rho pi d1, but we also have pi d1 square into 4, and u star is there. So, let us strike out things. So, once we do that, let us now also transpose out all the terms. Now, we have this u1, we transpose this on the other side, okay, and then we transpose this guy also on the side. So, we finally arrive, but we are not quite there. I mean there are few more things to be done, and no prizes for guessing. We need to now linearize about rho. So, rho naught plus rho 1 tilde, let us say rho is this thing for the duct 1. Remember, we are still in the duct 1 region. So, that is basically we are in the region somewhere here, okay. And u1 is nothing but, obviously this is u1 tilde, but like I said, we will have a mean flow, okay. So, we can just say let us say this is u naught, because we promised there will be no flow in the annular cavity, at least for the configurations, at least for CTR configuration. Other configurations we are like cross flow elements, different cross flow expansion contraction element or the reverse flow expansion elements, they may have some non-zero mean flow in the annular cavity, but right now let us not sort of bother too much about that. let us just sort of analyze these configurations, that will be good. So, let us do that. We get this. So, basically what will happen when you do that, del del rho naught of t, this will be 0 because this does not change. So, we will just be having rho 1 here, and again if we use our old techniques, rho 1 tilde and u naught plus u 1 tilde, and let us go back to our week 1 lectures where we talked about the principles of linearization. I mean, different arguments that we put forth to linearize things. So, we would basically get, this is definitely a second order quantity, this one, so this will cancel, and this does not vary with space. So, this will also sort of vanish, but what we are sort of really left with is rho naught into u 1 plus rho 1 tilde into u naught. So, in this particular thing, and here of course, we will have an extra term rho naught plus rho tilde and all that sort of a thing. So, we will worry about that in a bit. What we have to do really is that just simplify this equation. Here we will get this thing in, because by the arguments that I put forth, and this entire thing will go inside this bracket. So, del del z of this guy is 0, del del z of rho naught. So, rho naught you can take it out. So, I will just directly write rho naught, and what do we get here, u 1 tilde, is not it? We get this guy, and here we get u naught is again taken common, and we get this is rho. Okay. And this particular term is a too small quantity. So, we choose to sort of ignore this term, and then we have additional term, that is your 4 times rho naught. So, rho naught plus rho tilde, we will sort of ignore rho 1 because that is rho 1 tilde because that is too small, and d 1 and u star, that is u star is nothing but the radial velocity. So, here we finally arrive at the equation. So, you can also have a look at the book by Professor Munjal, in which these equations are sort of directly given, but what we did now was a detailed proof of the equations. Similarly, now one thing I will not go to the derivation again, but directly because of lack of time, I will just directly write down the momentum equation in the duct 1. So, momentum equation will not change. It is again, like I am repeatedly saying, the perforate just serves to act like a medium of transferring the acoustic fluxes. So, basically whatever changes or additional terms arise, they will arise in the continuity equation. That is why only the continuity equation is affected. So, if u star is 0 in case of a solid wall, you get back your old equation. So, let me just expand this guy out. So, this is your this thing. So, this is something like this, and what we can also do concurrently is assume isentropicity. So, when we do such a thing, what we basically get is we sort of get things like P 1 and 1 by C naught square. Okay. And here also we get C naught square, and instead of this thing we get P 1. So, I am directly sort of writing this 1 and 2. Now, basically what we do before we actually move ahead, it is sort of pretty instructive if we could further simplify equations 1 and 2 at this stage, by assuming time harmonicity, time harmonic solutions, and another thing is directly talk about what u star is. So, if you go back to our control volume, the median 2, fortunately in terms of algebraic simplifications, this will have only the u2 term, u2 tilde term present, okay, and this will not have any mean flow, at least for CTR. So, additional terms will sort of drop off. u2 tilde will only be there, but what about u star? There should be a relation between u1, u2, or actually P1 tilde and P2 tilde and u star. So, basically as it turns out, you know, this u star is nothing but the difference. Here it is the first time that we are introducing the expression of perforate impedance. So, you know, we will talk about all this thing perforate impedance later on, but u star is nothing but P1 tilde, which is a function of z. I am not, this is supposed to be z, something like this, but I am not writing z, it is understood. So, P2 tilde divided by rho naught C naught zeta. So, in other words, the perforate impedance, that is the opposition that the perforate surface offers to flow, is P1 tilde minus P2 tilde divided by rho naught C naught u star. Okay. So, this is what we get. Now, we will use this equation, let us call this as equation 3, is equation 1 and 2 already I have talked about. By putting or insisting time harmonicity and using equation 3 in equation 1. So, basically we need to simplify these equations. I have already written down these equations. So, how did I get this? So, term by term we need to sort of simplify. If we go back, if we put, you know, P1 tilde is your nothing but insist time harmonicity. So, once you assume this, and obviously we need to solve in space. So, when you do the derivative, it is pretty simple, straightforward, that you will get this term with P1 tilde to be understood as a function of z, and e j omega t, all the variable always have this e j omega t. So, that will factor out, and same thing will apply here. So, we wherever temporal derivatives are there, we will replace that by j omega, and with the understanding that I have talked about now. And so, as a result, there is only one variable that is left, that is z. So, the PDs will then be converted to ODEs. So, del z term will become ddz. Okay. And another thing that we have done directly in the equations that I have shown here is that you can clearly see this guy P1 tilde minus P2 tilde divided by rho naught C naught zeta. So, this is substituted equation 3 in the equation 1, and we have just left it in this form for now, but we will obviously need to process the equations further. And another thing is that u naught by C is m naught. So, m naught divided by C naught, that is what sort of we have. Let me do some live simplifications here. So, we multiply by sort of C naught everywhere, is C naught, and this guy will go away, and here there will be just C naught. So, what is omega by C naught? That is your K naught, j times K naught. Okay. And we multiply it throughout by C naught, isn't it? So, so basically your this term will also go away, and this will cancel out, isn't it? Because if you look back at your this expression rho naught, and here we had this expression. So, rho naught directly sort of goes away, and we are left with this. So, we can just leave it like this for now. This is probably one of the most simplified forms, and we probably would have to rearrange a few things here and there. So, that is what we will do. In this particular momentum equation, what we can do is multiply the term outside by C, divide by C naught. So, this will become K naught, this will become m naught. Okay. And we can, you know, further divide the entire thing by rho naught C naught, that is like your normalization values. So, we can sort of do that, but you know there is one good thing about say equation 4 and 5 is that it is in the form of a coupled linear ODE. So, what are the variables in 4 and 5? P1 U1, okay, and P2 is of course there, and then we would also need, you know, as it turns out we have 3 variables, and you know P1, P2 and U1. But then in the annular cavity there will be continuity and momentum equation also, and there will be a term containing u star in the continuity equation. We need to eliminate that to get 2 more you know such equations. So, then we will be having 4 equations and 4 variables. So, then we will you know sort of will be in a decent position to put that in the coupled you know x dot is equal to Ax kind of a form. X is a state vector and x dot means with derivative, spatial derivative. So, let us go back to our control volume what I had drawn here. So, you know what, so basically we are referring now to this region, just outside. So, what is the, the other thing remains the same. So, we need to speed up our derivation. There was 0 mean flow, like I have been insisting for CTR, and the flow that goes inside. Now, this is rho S2. Now, what is S2 by the way? S2 is, let me make it clear here, this is okay, this is here. So, this is what it was. Now, but S2 remains uniform, as I have been mentioning. So, we will keep this guy aside and go about our business of simplifying things. So, rho S2, let us say U2Z. Now, I will just write down few things, assuming that you guys are now sort of very well acquainted with the derivation, the way it goes. The one that enters the stuff here, the one that goes out here, and then there is a contribution, that there is a term that comes inside, isn't it? And then there is, we need to balance it with the temporal changes that's happening inside. Okay. So, as a result of all these things, let me just finally write down, I will not do the control volume thing again, in the sense I will not do this business again for lack of time. So, what I will probably do is directly write down the linearized form for the annular cavity of the continuity equation, assuming 0 mean flow in the annular cavity. So, here we have your rho naught and this thing, isn't it, minus 4 d1 divided by d2 square by d1 rho naught, and this is your u star plus okay. Now, we as usual we put our this expression P1 minus P2 divided by this thing in here, and also sort of simplify things by assuming the following form. So, this is rho naught, what was it? It was P1 minus P2 by this guy becomes j omega rho 2, but keep in mind that rho 2 is nothing but your P2 by C square, P2 tilde by C naught square. So, let us do some simplification and multiply all the entire thing by C naught. So, multiply by C naught. So, this goes away and this thing is like this, and this will become okay plus j times K naught P2. This is what we will get. Okay. Initially, you had C naught square, we divide rather we multiply throughout by C naught to get this kind of a thing. Rho naught here cancels out and you multiply by C naught. So, C naught is cancelled out once you multiply C naught here, this gets cancelled with this one, and there is only a C naught square, so only C naught survives, and omega by C naught is K naught in this term. So, well, we get this equation, and let me number this as equation number 6, okay, equation number 6. So, it is clearly an ODE, and we have 3 variables P1 tilde, P2 tilde and U2 tilde. So, we have basically 4 variables P1 tilde, P2 tilde, U1 tilde, U2 tilde. We have managed to successfully eliminate U star, the coupling, the radial velocity that goes, radial acoustic velocity that goes out of the perforate thing. Okay. So, because of that we now have your equations here. Now, what happens to the momentum equation? Momentum equation will be the same as in duct 1, the inner duct, but just that your mean flow is not there. So, we just have this guy minus P2 by Z. Okay. So, again let us sort of simplify things. So, this will become j omega u2 is equal to minus dP2 times dz. So, rho naught C naught j naught u2 tilde, and this will become like this. Okay. We probably can name this as equation number 7, probably the most simplified equation of all the equations that we have seen so far. So, here of course, this was also simple, but only thing was that mean flow velocity was there. Now, we clearly have 4 equations, equation 4, 5 and 6 and 7. So, for this thing, how do we go about doing the stuff? So, what we probably can do is that put that in the form of x dot is equal to a x. What is x dot, or what is x for that matter? X is nothing but state vector. You can define it something like this: P1 tilde normalized form U1 tilde P2 tilde rho naught C naught U2 tilde. So, dot means with respect to, or you can actually instead of dot, a better way, dot usually means with respect to time, but I guess this is a better way. So, ddz of this thing, that is this particular form has to be solved. So, it is ddz of x is equal to A, where clearly A is your 4 cross 4 matrix. Let us populate the matrix. So, basically from equations 4, 5, 6, 7, that is 4 to 7, from 4 to 7 we need to get to this form, basically to get the form of A. Let us write down the equation A like this. First is the continuity equation, second is your momentum equation for duct 1. So, let us do a systematic job. It is going to be a bit tedious. So, I would request you guys to bear with me. I may make some occasional sort of mistakes. So, in that case I will have to do it some part again. Let me sort of make equal spacings 3 and 4. Okay. So, this is it's understood that the first row is the one continuity in duct 1, momentum in duct 1, continuity in duct 2, momentum in duct 2. So, well, this is nothing but I should have drawn dotted lines. Okay. So, now let us fill in the different entries. Okay. So, basically what we need to do is that find out A11 element. So, for that we probably have to go back to slide 8, where we another thing that I want to tell is that do not worry about the terms this one and these two terms here. These are the mean flow terms which kind of poses a little bit of difficulty in solving the thing, in the sense that ddz of the state variable, that also will be a matrix. There will be slight modification to that. I will get back to that particular part in a while, but here you have j k naught. All right. So, now let us worry about populating the A matrix, and then whatever suitable adjustment we need to make to the ddz term on the left hand side, we will do that at a later stage. So, j k naught will be coming in here, plus there is a clear contribution by the term the encircled term in here. Okay. What is going to happen, you really have to take this on the right hand side. So, this will become minus j k naught and minus j k naught, let me write using this blue color, minus j k naught and minus 4 d1 by zeta. Okay. We will sort of get that. Okay. So, remember one part, that this is the entire thing is going to be multiplied by P1 rho naught C naught U1 P2 and rho naught C naught U2. We will get that sort of a thing. So, this is what will happen in here. Now, going back to the slide 8, remember we have we are done with the P1 terms here. Don't worry about the derivative here. Another thing that I must mention in here, because we are choosing the variable something like rho naught C naught u here. So, we will take this entire thing inside. So, because rho naught C naught or the characteristic impedance will not depend on the derivative. So, that is like a constant. So, the variable will be ddz of rho naught C naught u1. So, rho naught C naught u1 is essentially taken as one variable. So, well, this term also will not have any contribution in the A matrix. This term will not have, this will come in the left hand side. I will get back to that. Other term that will probably have a contribution is plus, mind you, plus 4 divided by d1 zeta, because you have to take this on the other right hand side. So, here it will be 0, because this will be multiplied by this guy, and like I said, this will be 4 divided by d1 zeta. I guess I made a mistake here, so sorry for that. It is 4 divided by d1 zeta, okay, and here will be 0, because there will be no u2 term. We will worry about this term and this term sort of at a later stage, but now let us also worry about the equation 5, that is a momentum equation which constitutes the second row. So, ddz and these two terms will be on the left hand side. Only term that contributes is minus j k naught. So, basically your minus j k naught has to be transposed on the right hand side, that is why it will become minus rho naught C naught u1. So, basically here you will have minus j k naught, everything else will be 0, is not it? Just sort of let us verify, and because calling this rho naught C naught u1 as one variable, is not it? So, we are done with the second two equations C1 M1. Now, let us worry about the other part, that is the continuity equation in the duct in the annular part. So, basically that is your, I guess, this equation, is not it? So, what are the terms that are contributing for the third row? Well, this we will worry about at a later stage on the left hand side, and this so only terms sort of here that are contributing is minus j k naught, minus j k naught for P2, we have to write that. Let us get back to your this thing, minus j k naught. So, what else is contributing to P2? So, here you have your minus minus plus, the plus will become sort of minus when you sort of transpose it on the other side. So, minus 4 d1 by d2 square minus d1 square zeta, okay. So, you will sort of have this thing here. What about the other terms that are going on in your equation number 9? So, P1, P2 is there, P2 we have sort of taken care of. So, the term that is associated with P1 tilde. So, here is minus. So, once we take it on the other side, it will be just plus. So, plus on this matrix. So, here we need to write 4 times d1 divided by d2 square minus d1 square and zeta, okay. Everything else will be 0, everything else will be 0. Why? Because there will be no contribution from u1 term and u2 term, and only thing now is remaining is your this guy, this equation. Now, this is fairly simple. What we will do is that we will sort of put a minus sign in here, and so they will become minus j k naught. And where should minus j k naught come? It should come on somewhere here, because this is multiplied. So, this 0 0 0 0 is multiplied here, 0 here, 0 with P2, minus j k naught with this. So, we have your A matrix, but remember there is more to be done. Now, this you have a particular form, let us make some suitable amendments. I will write this as a B matrix, and this B matrix is really your 4 cross 4, 4 cross 1. We will eventually be getting with 4 cross 1 matrix. So, this entire thing is ddz operator is operating upon this. So, what is the B matrix really? So, I will just need to rub this guy, and let me define B matrix here itself. So, it is something like this, okay. P1 rho naught C naught u1 This is not, this I am just writing to remind myself that things are, that is how the things will happen. So, we need to get back what are the derivatives, all the derivatives, the ddz terms were really in here. So, the continuity equation, is not it. So, here we have ddz of p. So, only term, only thing that would matter here, this is your m naught and here will be 1. So, what I am saying is that m naught has to be there, m naught will be there, and in place of this there will be just 1, it will just be 1. So, this is m naught and this is 1 0 0, m naught and 1. So, all the other things are not there. Let us come to the second row. So, ddz of p. So, here of course, there will be 1 and in place of this will be m naught, but hang on, we also need to do little bit of simplification. Remember, our variables are rho naught c naught. So, there is one thing we also need to figure out, that rho naught c naught is also multiplied by throughout here. So, rho naught c naught will go here as well. So, this will be clubbed in here. So, this will become 1 and this will become m naught. So, going back here in slide 8, these two terms are there and rho naught c naught u1 is sort of one variable, and this guy anyhow will be transposed on the other side. So, that is how we get your minus j k naught here, but in this thing you have your m naught, okay, m naught. Now, we have to worry about this guy, and I think there are no prizes in guessing. For the equation 6, this was sort of fairly straightforward. The only contribution that was coming was from this thing. So, ddz of u naught, u2. So, basically, here we have your 0 0 0 and 1. This was 1, because you remember this is only thing is the term associate this, once you take this thing inside here, the coefficient is 1, okay. And for this guy, this was minus transposed in here. So, again the coefficient is 1. So, for 1 this is 1 0 0 0. Clearly, when you have m naught to be 0, then you get back your familiar sort of equations. What we really get back is, when m naught is non-zero, of course, it needs to be there, but in case it is 0, so what we get back is 0 times p1. So, and so that is 0 and all, there will be no contributions, only thing that will be there is 1 times or just rho naught c naught u1 here, and then your p1 and this is also 0 0. So, this will be just be p1 ddz of p1 because of your momentum equation, and these things are also fairly straightforward. So, basically in case of m naught to be 0, which is your case of a stationary medium, we would sort of get back the state vector that is being given here. In case m naught is non-zero, we need to sort of invert this matrix. Since m naught is not dependent upon the spatial variable z, so what we can do is basically multiply throughout by B inverse, because m naught will not be a singular matrix. So, multiplying throughout by B inverse, we will get B inverse A. So, once you multiply B inverse B will be identity matrix I, and B inverse A will get us thing. So, let us do that. So, dd z of the state variable x is equal to B inverse A. This is 4 cross 4, just to remind you guys, 4 cross 4, and what was it? This was your x vector, isn't it, which is your 4 cross 1, where x, let me put it here again for you guys, p1 this was something like this. Once there is also one more thing what I would like to just mention in here. So, in case we chose rho naught c naught 1 as the first variable p1 here, so this minus j k naught would have been here and everything else would be there, and these things would have sort of shifted. But what other thing it would have done is that this would have been 1 and m naught in here. You see m naught is multiplied by P1. So, in case just if we switch things, so 1 will be here, m naught will be here, and same thing 1 will be here and m naught will be here, and this guy 1 would be here and this thing. So, it would have become a bit more easier to understand that, well, m naught is 0, then we would naturally get back your identity matrix, but this is just the manner we choose P1, taking P1 and M0, C0, U1 first. The idea is that after doing all this algebra, we have A matrix and we have your B matrix. So, let me call this equation, well, star, and equation this is double star, okay, equation star and equation double star, and finally we have your this matrix. Let me call this equation triple star. So, this is really a set of coupled ODEs in the 4 variables what I have mentioned in here, P1 rho naught C naught U1, P2 rho naught C naught U2. So, there are different ways of really solving it. This is one way, and if we were to do by the hand calculation, it will become very tedious. It's 4 coupled ODEs, like I said. Depending on the perforate impedance, it might be a strong coupling. So, generally people go to computer programming, MATLAB, for instance, or Fortran or whatever one is comfortable with, and get inverse, define the matrices, compute basically your inverse. In MATLAB what we would do is basically do inverse B multiplied by A, okay, A matrix. And once we do that, ddz of this, then there are things like matrix exponential. Matrix exponential one we can simply evaluate. So, the solution will be x, the x vector will some exponential times matrix into some constants which we need to eliminate by appropriate boundary conditions. So, we can solve a simple MATLAB program, at least for the case of a 0 mean flow. In MATLAB we can demonstrate that by kind of integrating this matrix using something like exponential exp a over whatever length we are kind of integrating. So, length of this guy, the perforated section that I am talking about here, let us say the total length is L, okay. So, since it is all uniform, it is a constant coefficient differential equation. So, we would get your e to the power exponential e to the power m exponential m exp m al. We will demonstrate that shortly in MATLAB, at least for the case of 0 mean flow and possibly with some value of non-zero mean flow. And then we can for a fully perforated thing, I will just demonstrate the MATLAB code, talk about the boundary conditions which are eliminated and explain them later, and get the transmission loss curves for a fully perforated section using certain perforate impedance expression. But before I do that, I would also mention couple of points. First is, this is one way of solving. Another way is analytical kind of a thing, in which basically what one does is really solves, you get 2 coupled second order ODEs in where you eliminate your U1 and U2. So, the variables are P1 and P2, and based on the mean flow present or the perforate impedance, the coupling can be strong or they can be sort of weak, and you can get your that equation can be further combined into one equation, that is your 4th order ODE, and then you can go about solving that thing using your characteristic equation and all that, getting 4 different linearly independent solutions. So, that is going to be quite tedious, especially when flow is there. So, I would not even bother going into that, but at the end of the day, when you are using your this function exponential, the MATLAB what it is doing, it is relying on the eigenvalues and the eigenvectors. So, the other way of course is to do not rely on this thing and find out the eigenvalues of this coupled equation by yourself, and then do the simple linear algebra thing, xi inverse lambda xi, something like that. But we will probably, to make it simple in this course, we are using MATLAB. So, we will do exponential m times AL, A is a matrix, or B inverse A, L is the length of the perforated section, and then this will be multiplied by some arbitrary constants to be determined. So, what we are going to do now, that at least for the concentric tube chamber, let us worry about the boundary conditions that will happen at the left hand right boundaries, whether it is a fully perforated thing or a partially perforated thing, and then I will for a certain couple of, by taking certain perforate impedance expressions, I will do some MATLAB calculations, or probably I will worry about the different perforated impedance condition and then present you some MATLAB results. So, all this we can have a look at in the lecture for the next week, that is week 8, and that is how we will go about solving before doing some parametric studies even for the external inlet and outlet case. So, thanks a lot. I will see you in week 8.